So in this problem, you are asked to predict the product that's formed when this compound, which is an acetal, is treated with acid. So an acetal is a functional group where the carbon has 2 sigma bonds to a heteroatom. So 1, 2. This carbon is effectively at an oxidation state of 2. So again, all we're doing is counting the heteroatoms, 1, 2. So because they are both sigma bonds, it's an acetal. So an acetal is functionally equivalent to a carbonyl. And what that means is when you treat it under acidic conditions, it's going to deprotect that, and that carbon is going to become a carbonyl. So the product that's drawn here is correct. You end up with this keto alcohol, and then this alcohol, methanol. So basically, if we're looking at the acetal carbon that's at the oxidation state 2, which I've highlighted as a blue dot, and you look at the non-oxygen groups, so the non-oxygen groups that are bonded to this, they're both carbon, so we can tell that's going to be a ketone. And the fact that if we trace along this skeleton, that this oxygen is bonded through the backbone, that it's retained in the ketone molecule. So this is the correct product. So the question was, how do we get there in terms of the mechanism? So the first thing I want to do is put some color into these different oxygens and show you where they go throughout the mechanism. So this oxygen becomes this oxygen down here in methanol. The ring oxygen, which I'll highlight in blue, becomes this oxygen. And then with green, from the acid, that becomes the carbonyl oxygen. So the first thing we do, we're under acidic conditions. So we're going to protonate. This oxygen. You can protonate either one, because ultimately you'll end up with the same thing. But let's just protonate this one first and show how the mechanism proceeds. So this is a proton transfer. So we've protonated. Now what we're going to do is elimination of methanol. So you can see immediately that's where we form the methanol. Now we form this oxonium ion, and so I'm going to draw a resonance form of that. And so this tells us that's an electron-deficient carbon, so we are in the presence of water from the hydronium, so that will attack. Now what we're going to do is a series of proton transfers. I'm going to show 2 at once, just to save some time here. So let's have water act as the base to abstract that proton. Then we're going to protonate this oxygen. So we end up at this stage here. Now we're going to do another elimination where that oxygen is going to push out that as the leaving group. It's leaving, but it's still retained in the molecule because it's bonded to the backbone. And then in our final step, to get to the final product, we'll have water act as the base to abstract the hydrogen. And so that's equivalent to the final keto alcohol. So let me just color in these oxygens again as the mechanism proceeds, so you can see where they end up. So the ring oxygen is the blue one throughout. And then the green oxygen, which comes from the water, the hydronium, is the one that ends up as the ketone carbonyl oxygen. So really in this mechanism of acetal to ketone, everything's in equilibrium. So you can go forward or backwards throughout. So the big thing is to understand these proton transfer reactions.